Okay, this is the end of 4.2. This is composite functions. So a composite function is like you take an input, you put it into one function, alright, and then you take that output of that function and you put it in to the next function. Okay, so basically, like, input goes in to which one comes first, and then the output of that one becomes the input of the next one. Okay, this is the notation that's commonly used. It says f of g of x. It looks like the letter fog or the word fog, but it's actually f of g of x when you see that notation. And again, it's still not multiplication, it's just function notation. And this is the notation I like, because it looks more like what's going on. X is inside of g, and then g of x is all inside of f. Okay, so that's function notation. Now, these give us like visual diagrams, just to kind of have a visual if you're a visual learner. Input goes in, this whole box is like the major function. That's the composite of the two functions. But x goes into g, g spits out g of x, and then that goes into f, and then f spits out f of g of x. Now, if the order is different, then we have a different order that would go into the functions. If it's g of f of x, which is what this one down here is, now the inputs go into f first, alright, and then the outputs of f go into g, goes into that second, alright, and then we get the overall output, and that would look like f of x going into g, alright, which is g of f of x. Okay, so there's a couple of visuals just to kind of give you an idea of what's going on here, but the main idea is that we've got something going inside of something else. Okay, an input becomes an output, and that output turns around and becomes another input. Alright, so here's just another visual, a way to think through this stuff. There are two machines in a room. One squeezes oranges to make juice. The other one is a canning machine that puts the orange juice into cans. Thinking of the two processes as functions, which they are, they have inputs and outputs, we name the squeezing function g and the canning function f. Okay, so this literally means an orange goes in. Alright, what are we putting it into? First, we're putting it into g. Alright, what is g? G is the squeezing function. So we take this orange and we're putting it into g first. G is the squeezing function, so we're going to have something come in and squeeze this orange. Alright, and then its juice is going to fall out. So here comes the orange juice. Okay, and then what's f? F is the canning function. So it's going to collect the juice. Okay, what's going to happen with g of f of x? Now we got the orange. What's going into first? It's going into f, the canning function. So now the orange is going into a can. And then what are we doing? After that, we're going to g. G was the squeezing function. So now we're going to squeeze the can that has the oranges in it. Okay, that doesn't make any sense. Alright, I mean, it makes sense. This is what it means, but we wouldn't do that. Okay, so this one is the only one that makes sense in context. Okay, so what this is supposed to illustrate is that composite functions are not the same if the order is changed. F of g of x and g of f of x are not the same thing. Now, that's not to say they're never the same thing, but it's extremely rare that these two things are the same. Alright, so f of g of x is not the same as g of f of x for most cases. Now there will be some cases we'll study later on where they are, but extremely rare. Alright, so this is a typical type of problem. We got these three functions, okay, and we're going to create a domain of each of these new functions formed, as well as to form the functions. So I'm going to start with a, h of f of x. Alright, what does that mean? It means put f of x into the h function. Alright, well first we need to study what h does to an input. Remember, what function notation means is a set of instructions. What does h do to an input? It puts that input in the denominator with a numerator 1. So it puts the input into the denominator with the numerator 1. Well, what's the input? F of x. So f of x goes in to the denominator of a fraction with a numerator 1. That's what h does to any input. It just so happens that the input this time is another function. Alright, and now we go up here and we look and see f of x is 2x minus 5. So we're going to replace this with 2x minus 5. And we get 1 over 2x minus 5. Alright, so there's h of f of x. Now give the domain. Remember, this has division. 1 divided by 2x minus 5. We can't divide by 0, so we need to figure out what causes that denominator to be 0 and then not allow that to happen. Alright, well, add 5 to both sides. We get 2x is equal to 5. Divide both sides by 2. Right, and we get the domain restriction. X can be all real numbers, but x cannot be 5/2. Right, or if we write it with interval notation, negative infinity 5/2, parentheses, union, parentheses, 5/2, positive infinity. Alright, now part B wants me to find f of g of x. So we're putting g into the f function. Alright, what does f do to an input? F doubles the input and subtracts 5. So f doubles whatever the input is and then subtracts 5. Alright, well what's the input? The input is g of x. So we're going to double g of x and then we're going to subtract 5. Alright, well g of x is 6 minus x squared. So we're going to replace that with 6 minus x squared in that parentheses, and we get 2 times 6 minus x squared minus 5. Alright, this, again, just so you'll see it, this is g of x. Okay, and what does f do to an input? F doubles the input and it subtracts 5. Alright, we're just combining these two things together. This goes into this. This is what f does, doubles it, subtracts 5. So we're putting this other function into the f function. Alright, from here we need to simplify. They want us to simplify these once we compose them. So I'm going to distribute that 2 through and get 12 minus 2x squared minus 5, and then 12 minus 5 is 7 minus 2x squared. Alright, domain here. There's no division, there's no root symbols, so our domain is all real numbers. Or if we put it in interval notation, negative infinity to positive infinity, we can put anything in there. because there's no division by 0. Alright, and then the last one we got g of f of x. So we're switching the last one that we did around. So this time we're putting f into the g function. What does g do to an input? It squares the input and then it subtracts it from 6. So g squares an input and then it subtracts it from 6. Right? What is the input? The input is f of x. So we're going to square f of x. Alright, again, what is f of x? 2x minus 5. So that's what gets squared. Alright, and then we have to remember, 2x minus 5 squared is not 4x squared minus 25. We have to FOIL this out. This means 2x minus 5 times 2x minus 5 again. Alright, and then we FOIL it. 2x times 2x is 4x squared. 2x times negative 5 is negative 10x. Negative 5 times 2x is another negative 10x. And negative 5 times negative 5 is positive 25. Okay, so that's what this is, but remember we're subtracting this, so we still need parentheses. Alright, I'm combining those two, minus 10x to minus 20x, and then plus 25. Now before I subtract, I've got to distribute that minus sign through. Alright, people did a lot of this, made this mistake a lot of times on their labs last week. Distribute that negative through. So 6 minus 4x squared plus 20x minus 25. Alright, and then last step, combine your like terms. So we get a minus 4x squared plus 20x. Alright, and then 6 minus 25 is minus 19. Alright, and there's our composed function. Right? Domain of this, again, no division by 0, no radical symbols to worry about, so we get our real numbers once again. Alright, negative infinity to positive infinity in interval notation. Alright, so that's 4.2. The next video is going to be a couple of examples from the work, the homework, and if you have any questions after that, just send me an email and I'll get back with you.